Good evening. This will be our last podcast in Chapter 5, and tonight we're going to talk about real gases and talk about how they're different than the ideal gas law that we have been studying this entire unit. So it says that no gas exactly follows the ideal gas law except if we are at low pressures and high temperatures. That's something that you do need to keep in mind. Low pressures and high temperatures, then we can go ahead and say that gases mainly behave ideally, which is Pivner. And the reason for that is that at low pressures, there's less interactions. High temperatures, we're overcoming those interactions, and that's what happens there. So if we take a look at a few plots of this to prove and show you what we are discussing here. So we have a plot of PV equals nRT, so the ideal gas law versus different pressures for several gases. Now you can see here that at very low pressures, 1 atmosphere is low pressure, that all these gases are behaving ideally. Then we go out here where we have 1,000 atmospheres, which is a very high pressure. You can see that the gases are beginning to deviate. Why is this? You should be thinking, well, they're bouncing around each other. There's more interactions. They have some attractions that are going on here when you're creating a lot of pressure. So to take a look at another plot when we are involving temperature, nitrogen at 3 different temperatures. So you can see that as we increase the temperature, the gases become more ideal. And the reason for that is that they're overcoming any interactions that they have. So the temperature is way too high for them to have those interactions. Again, we have low pressure. They're behaving very ideally at low pressure and at high temperatures. Okay, so you can see this, that, well, we must have to change our kinetic molecular theory and our ideal gas law. And the first person that started looking at this was Johannes van der Waal. And he was a physics person, and he actually got the Nobel Prize in 1910 for studying and looking at gases in looking at the correction factors needed. So the first thing that he found is that real gases actually take up some space. And so these are one of the correction factors that he did, and you can see that the number of moles of a gas is going to relate to the deviation depends on the molar mass and the size of the particle. That should make sense to you as we think back to the semi at the stoplight versus the sports car scenario that I was talking about in the last podcast. Point 2 that he found is that real gases allow for attractions that occur among particles. We know that water vapor, for instance, has charged ends, and so it's attracted and it's creating these attractions. And so we have to have a correction factor for this. And so you can see that it gets very complicated very quickly. So the correction factor depends on the concentration of gas molecules, moles of gas particles per liter. Well, that should make sense to you. If you're thinking about the per unit volume, how much space there is, how many gas particles are in there depends upon the amount of interaction there is. So here's just a simple little scenario that your book talks about, that we have a gas at low concentration. There's not very many interactions. So in this situation, you should be thinking, well, these gas particles probably behave more ideally. And you would be correct. There's fewer interactions. They are providing some pressure onto the wall, but they're going to act more like Pivner. So this one is going to be more ideal. And when we say Pivner, remember, we're thinking ideal gases. Now, if we take a look over here, we have a higher concentration. There's going to be more interaction between the molecules and the particles. And so there's actually going to be lower pressure on the wall. So this one's going to have low pressure because we have so much interaction going among the particles. They're bouncing off each other, and they might have many, many collisions before they eventually hit the wall. So more interactions, lower pressure on the wall. Now, if we take a look at another scenario here, that pairwise interactions among gas particles, meaning that if I have one particle here and I have a total of 10 gas samples, that we're going to have some attractive forces here. We're going to have some pressure created because of all the collisions that are going on, and we actually have 45 pairs that could happen here. So yes, there's going to be some interaction, there's going to be some attractions, and it's going to move further and further away from the ideal gas law. So van der Waal thought of all of these situations, talked about the pressure, the volume of the container, the um, the correction factor depending upon the volume of the container, how many particles that are in there, and you can see that the higher the interaction, the more deviation from the ideal gas law, which is what we were talking about. So Van der Waals took all of this into consideration. Now take a look at this formula. Is this something that you're going to want to study day in and day out to really take a look at gases, or would you rather do PivNert, which you can see PivNert is here in a little form right here with all these corrections added. So this is why we are studying gases in the ideal gas law, just because it's very difficult to take a look at all these factors. Sorry, I'm at home if you can hear my phone ringing. Okay, so Van der Waals equation. It says this equation corrects the flaws in the kinetic molecular theory. So in the kinetic molecular theory, we talked about that there is no interaction between the gases. And so we are able to study with PivNert. So this correction explains real gas behavior and provides confidence to understand the fundamentals of a gas behavior. Good important chemistry takes place in the gas phase. There's tons of things that we can study here, but we want to study it in the ideal gas world just because it's a lot easier for us. And again, you can take a look at comparing it. If we want to correct it again from the real and bring it back to the ideal gas law, this is what you would need to do. And you can see somewhere in here that we still have PivNert, we have pressure, we have some volume, we have nRT. So we're taking the ideal pressure times the ideal volume, and then we would be relating it to the ideal gas law. Again, this is all experimental behavior. It's something that's very difficult to do, and so we're just going to disregard all these corrections and take a look at PivNert. Okay, let's see, sorry about that. So our last slide that we have here, again, if you are just applying the gas law and looking at this pictorially, you can see the volume taking up the gas particles right here, that this one is going to behave more ideally. There is less pressure, we have more space for the molecules to interact, and so there isn't going to be the attractions between the molecules as there will over here. We create more pressure. If we have the same number of gas particles, this is going to deviate more from PV equals nRT because I have a smaller space, I have greater pressure. So again, we were talking about that the volume and the temperature and the pressure of the particles are all important trying to understand these gas particles and how they interact. But let's just try to keep it simple and stay in the world of PV equals nRT. So we don't need to be a real gas, I guess. All right, so you guys have a wonderful night, and I will see you in class, and we will probably be testing sometime this week. So be working on your problems. You have a wonderful night. Take care.